Okay, hello everybody. This is the recording for the higher questions for radioactivity that I've just set you guys to go through. This is the answers. So, looking at these first ticking box questions, we have got to find out or define which statement is true about alpha particles, about beta particles, and about gamma rays. So firstly, the first question says, what is an alpha particle? Tick one box. So we've got multiple choices here. Remembering back from our lessons, an alpha particle is two protons and two neutrons joined together, essentially like a helium nucleus. So this is two positively charged particles and two neutrally charged particles. The only one that talks about 2 and 2 is our first one, two charged particles and two neutral particles. So that is our answer to question 1A. Question 1B, if I just slide the page up a little, says which statement is true about beta radiation? Well, a beta particle is a high-speed electron. When a proton turns into a neutron by losing some negative charge, it kicks out a high-speed electron to wrong way around. When a neutron turns into a proton, it becomes positive by losing some negative charge, and that is the high-speed electron that is kicked out, that is our beta particle. So we've got our alpha particle up here, we've got our beta particle down here. Beta particle is the type of radiation with a negative charge then. This one has to be. Lastly, question 1C. Which statement about gamma radiation is true? Tick one box. So gamma radiation is an electromagnetic wave. It is not low frequency. It is very high frequency. It does not cause the charge of the nucleus to change or the mass of the nucleus to change, which means it has to be our answer all the way over up here. It has a very long range in air, which it does. It has the longest range of all types of radiation. Moving on next to question 1D then. This question is all about the Chernobyl disaster. And it says that the table below shows the half-lives of two of the radioactive isotopes that contaminated the environment. We've got cesium-137 with a half-life of 30 years and iodine-131 with a half-life of 8 days. The question then asks us, a soil sample was taken from the area around Chernobyl in 1986. The soil sample was contaminated with equal amounts of the cesium-137 and iodine-131. Explain how the risk linked to each isotope has changed between 1986 and 2018. So the first thing I'm going to be thinking is, okay, 1986 to 2018, how many years have gone by in that time? And then I can apply that information to how the half-lives will have changed over that time. So 2018, subtract 1986, will give me the amount of years that have passed. And the answer to that is 32 years. So let's think about how this is going to affect the risk from each type of isotope when they both emit the same type of radiation. So it's not that one is going to be more dangerous because it emits a different type of radiation to the other. It's going to be to do with this information up here, okay? Their half-lives. So looking at their half-lives, cesium-137 has a half-life of 30 years, iodine has a half-life of 8 days. Now if you think about the definition of half-life, that's how long it takes for the activity to half. So if I've got an equal amount of cesium and iodine in here, and they've all passed through the same length of time, the half-life of iodine is only 8 days. So every 8 days, the activity of that iodine halves, whereas every 30 years, the activity of the cesium halves. So 4 marks here that I need to be talking about. So it's quite a few things that I need to be thinking about and writing. The risk I'm going to talk about with cesium first, because that's first on my list. Risk of cesium 137 hasn't changed much. Now the reason why it hasn't changed much is because it's only gone through one half-life. So the activity has only just halved. So because it has only gone through one half-life. So, because it's only gone through one half-life, the activity will be quite high still. So risk of cesium-137 hasn't changed too much because it's only gone through one half-life. So activity still relatively high. On the other hand, the iodine, so the risk, here's my first point, here's my second point, risk of, or the risk due to iodine it helps if I can spell, iodine 131 has reduced significantly because it has been through many half-lives. So because it's been through many half-lives, so the risk of iodine 131 has reduced significantly because it has been through many half-lives. Its activity will be very low. Now, with this being a longer written question, you are getting 2 marks for each point that you have made. Okay, cesium 130, or for 2 marks for each of these 2 big points here. The risk of cesium is high still, won't have decreased by much because the activity has only halved. It's only been through one half-life. Okay, whereas compared to the iodine, the risk has reduced significantly with the iodine because it has gone through many half-lives, and the reason why it's been able to go through many half-lives is because its half-life is only 8 days. Okay, if you wanted to work it out, let's just say there's 365 days a year. Sometimes there aren't with leap years, but if I've got 365 days and it's been 32 years, 365 times 32 is 11,680 days. Dividing that by 8, it's been through about 1,500 half-lives, 1,460 half-lives. So the risk of that iodine, or due to that iodine 131, is massively decreased. Okay, now on to the last part of question 1, question 1E. Determine the year when the activity of the cesium-137 in the soil sample will be 1/32 of its original activity. Okay, so what we're saying here, if you remember, every time it goes through a half-life, its activity halves. So we are starting one half-life, half, so 30 years. Each of these halves is going to be 30 years. So half of a half is a quarter. So that's 2 halves, that's a quarter. Another half of a quarter is an eighth, so that's an eighth. Half of an eighth is going to be a 16th. And half of a 16th is going to be 1/32. Okay, so how many halves have I done? You got 1, 2, 3, 4, 5. So 5 half-lives in total. The way I've been able to work that out is I basically said, okay, well, how many times do I have to multiply by, how many halves have passed to get to 1/32? Okay, one half by itself is a half. Here I've got 1/4, then adding this makes 1 over 8, adding this makes 1 over 16, and then this final one makes 1 over 32. So that's 5 half-lives that have passed. And if 5 half-lives have passed, and each half-life is 30 years, I'm going to do 5 times 30, which is going to give me 150. But that's not my final answer. Determine the year, not how many years does it take. Determine the year when the activity of the soil sample is 1 over 32 of its original value. We're starting in 1986. 1986 plus my 150 years is going to give me the year 2136. So the activity of this cesium-137 will not have reduced or will not be 1 over 32 of its original value until we get to the year 2136. Okay, so looking at question 2 now, I'm going to turn over once I've just read through this. The figure below shows how the activity of a radioactive isotope changes over an 8-hour period of time. So what we've got is we've got a lovely little half-life graph that shows us how the count rate, the activity of a substance changes over 8 hours. Predict how long it will take for the count rate to fall from 100 to 1.56 becquerels. So what we need to think about here is I could try and look at 1.56 on this graph, but it's going to be impossibly hard to find because we are going up from 0 to 20 in one big box. So it's going to be really hard for me to read it off the graph. Okay, what it's wanting you to do here is it's wanting you to say, okay, well, how many times do I have to half this substance to get to 1.586? Let's work out the half-life. Okay, so the half-life, just reading a single half-life off the graph, nice and easy. We start at 100. Half of 100 is 50. So 50 is here. Take my ruler. You guys will have done this on your computer screens, hopefully, so you'll have drawn lines on your graph instead. I probably should be using a pencil, but it gets me to the right answer all the same. 50 read across. Camera is now in the way, but you can see that that is 2 hours. So I'm going to write off to the side somewhere. Make sure you guys can see off to the side over here. 1 half-life equals 2 hours. That's the first thing I need to do for this question. Okay? Now that I've found that the half-life is 2 hours, I need to say, okay, well, how many times do I need to half 100 to get to 1.56? Okay? So we've got 100. Half it once, it becomes 50. Half it twice, it becomes 25. Halving it a third time, it becomes 12.5. Halving it a fourth time, it becomes, that's a 12.5. Halving it a third time, 12.5 halved is 6.25. Halving it a fifth time gives me 3.125. Halving it a sixth time would then give me 1.56-ish. There we go, we've finally reached the point I'm after, and it took me 6 half-lives. Okay? If one half-life is 2 hours, 6 times 2 is going to give me 12 hours. And that's why you can't read off the graph, because the graph doesn't go as far as 12 hours, so therefore I wouldn't have been able to find that out. Okay, so what I've done is I've said one half-life is 2 hours, read that off my graph. If I'm starting at 100, I half it once to 50, halve it a second time to 25, halve it a third time to 12.5, a fourth time to 6.25, a fifth time to 3.125, and that sixth and final time to my 1.56. So that means 6 half-lives have passed. One half-life is 2 hours, so 6 half-lives is 12 hours. So there's my final answer, 12 hours. Okay, I'm going to do the next 2 questions together because this first one should hopefully be nice and easy. All we've got to do is remember our alpha decay to start with. This is one of the hardest types of decay equation questions you'll ever be given, because otherwise they'll have a bit more numbers on them and it makes it a bit easier. So lead-210 is a radioactive isotope that decays to an isotope of mercury, Hg, by alpha decay. Okay, it tells me it's alpha decay. Complete the nuclear equation to show the alpha decay of lead-210. It tells us that it's alpha decay 2 times. Okay, that's how important it is that it's alpha decay. So what that means is I can write my alpha symbol in there, and I can use that to say, okay, well, what are the numbers that go along with alpha? Now, if you can remember, this is one of those things that you do need to remember. Alpha is 4 and 2. Remember, I talked about it in question 1. It's 4 particles in total, 2 protons, which is where that 2 comes from, and 2 neutrons. Okay? So the numbers there are 4 and 2. You can write the alpha symbol. You don't have to. You could have written the helium symbol instead, because this is the same as a helium nucleus, an alpha particle. So 42He or 42A is absolutely fine, or should I say alpha, that's the Greek letter, absolutely fine for this bit. Now I've got that in there, I can do the rest of my maths. 80 plus 2 is going to give me 82. Something plus 4 is 210. So this one's got to be 206. And that's all there is to that first part, just some key stage 2 maths, as long as you can remember what an alpha particle looks like. Next question is a 5 marker, a bit more of a longer written bit. And what I've got to do is I've got to say, well, how can ionizing radiation have hazardous effects on the human body? So make sure that's straight for you. How can ionizing radiation have hazardous effects on the human body? You can't just write something like cancer for this and expect to get all the marks, okay? Cancer would get you one of the marks, but it's asking you to explain. If it said describe the hazardous effects of ionizing radiation on the human body, it would probably be a 1 marker. Cancer would be fine, okay? But we need to talk about, what alpha radiation or beta or gamma can do to the human body. If it's ionizing, it can turn atoms into ions. Ionizing radiation turns atoms into ions. Okay? Well, but explain. That's not an explanation, that's a description. Let's add more detail. Why is this hazardous to the human body? Well, that can break up molecules. And breaking up of molecules can change DNA. So each of these lines is a mark point, okay, for my 5 marks. So I've got 1, 2, 3. This can change DNA. Changing DNA, missed that off, which can change DNA. Changing DNA causes mutations to genes. And this can lead to cancer. Now, with one of these longer written questions, you wouldn't need to say exactly the same as what I've said. As long as you have words to the effect of something about atoms becoming ions because of this radiation, something about breaking up molecules, something about changing DNA, something about causing mutations, and something about cancer. That's what you would need to have for each of these 5 marking points. Okay, so last 2 questions now then, guys. Question 3. A radioactive isotope has a half-life of 10 minutes. At the start of an experiment, the activity of this isotope was 8,000 counts per second after allowing for background radiation. Calculate how long it would be before the activity fell from 800 counts per second to 200 counts per second. This is exactly the same as the question you can see bits of over here. I've got to basically work out how many half-lives it's been through to go from 800 to 200, and then how many times 10 minutes that is. So 800 halved once would be 400. Half again would be 200. So it's been through 1, 2 half-lives. So if it's been through 2 half-lives and 1 half-life is 10 minutes, all I'm looking at doing is saying, okay, it's 2 half-lives. I'm writing this down because if I mess up and make a mistake in my calculation, the fact that I've worked out 2 half-lives is probably going to be a marking point. So even if I make a mistake in my final answer, I'm going to secure myself 1 of the 2 marks by having done that. Okay, so I'm going to say 2 half-lives, 2 times the 10 minutes is going to give me 20 minutes. And I can write that down there. Question 3b then says, a physicist investigates a solid radioactive material. It emits alpha, beta, and gamma. The physicist does not touch the materials. Explain why the alpha particles are less dangerous than the beta and gamma rays. So, what we need to be thinking about here for 2 marks is how alpha behaves in comparison to how beta and gamma behave. Okay? The fact that he's not touching the material, she is not touching the material, means that the alpha particles are going to be either stopped by the air or by the person's skin, whereas beta and gamma can get through the air at the person's skin, and they're my 2 marking points. So alpha cannot get through air / skin. 1 mark. 2nd mark for saying, in fact this was a mark up here, and this was a mark as well. 2nd mark for then saying beta and gamma can reach or get or something like that inside of the physicist. And that might be bad because it might damage organs or cells or something like that. So beta and gamma can reach inside of the physicist, and I'm just going to simplify it down to say cause harm. So there's your 2 marking points for question 3. And with question 4 being a 1 marker, I may as well do it in with this as well. Question 4, technetium is produced by the radioactive decay of molybdenum. What changes occur in the nucleus of a molybdenum atom when this happens? So let's have a look at those numbers. I'm just going to write those a little bigger. 9Tc 4 3. Make sure you guys can see that. And that is becoming Mb9942. So what changes are occurring in the molybdenum atom, or the technetium atom, sorry, for us to reach that point? Oh, hang on, sorry, this is the wrong way around. Not doing very well here, am I? I was looking at that and wondering how am I meant to do that one. That's the wrong way around, that's why. So technetium is produced by the decay of molybdenum. And this is a decay equation. That's all this is. What is missing off of the end here? Well, the number on the top hasn't changed, so that would be a 0. And the number on the bottom has gone up by 1. So 43 plus something is 42. If it's gone down by 1, I have to be adding -1. And the radiation type that has a 0 and a -1 is a beta particle, which you can also represent with an electron symbol, which is an E. So either of those would be fine here. Writing the decay equation isn't necessarily the thing that will get me the mark. I need to say what happens. Okay, what happens in beta decay? If you remember on the past question 1, I said a neutron turns into a proton. Look at the numbers and it makes sense. The amount of nucleons inside the atom, inside its nucleus, has not changed. I've got 99 in both cases, so my number of nucleons has not changed. But I've got an extra proton. So that means one of these 99 nucleons, which is a neutron, has turned into a proton to increase my atomic number. Okay? So what has happened is a neutron has become a proton. Okay, I could have said something like beta decay. That might have gotten me the mark as well. Okay, but this is